Okay, hey there, this is Garrett, and we are now doing the CL-01 detecting and reacting to spikes tutorial. I'm just going to go refresh the page real quick, just so we can start from the top kind of fresh. As you can see, there was the little display there from the last time, but I also have the full visualizer available over here. So jumping in here, if we start by running this first cell, that's exactly what we went through in the CL00 tutorial, and it will show the visualizer right there. If we come down to cell number 1, which is detecting and reacting to spikes, this is a toy example loop that it loops 1,000 times per second for 5 seconds and stimulates any electrode where a spike is detected. So if we look over here, any electrode where there is a spike detected, these little green lollipops, is basically going to be stimulated. So let's run this real quick and then I'll explain. So you can see it right there, they're getting stimulated. Only the ones with activity are getting stimulated. And basically let's dive into the code here so we understand it. We start with 2 lines. The first line from CL, basically CL open. So detect and react to spikes. We import CL with CL open as neurons for tick in neurons loop ticks per second equals 1,000, stop after 5 seconds. For spike in tick analysis spikes, neuron stim spike channel 1. So you can kind of see there that first block of code, what we're doing. And this is the heart of the whole notebook below. So this piece is actually, it's not really going to do anything. If I run it, we can see over here, it doesn't really do anything. Okay, why is this? Well, the reason that this isn't doing anything is because, well, it prints to the console boilerplate example has finished running, and it did, for tick in neurons loop, ticks per second 100, stop after 5 seconds. It did a similar thing, but without the for loop to stimulate neurons.stim to stimulate those spikes in the channel. Okay, so this is the backbone. It's boilerplate code. It's the backbone of the whole shtick with the CL1, which is closed loop. It's closed loop simulation. And we're going to kind of dive in here to this piece of code, this boilerplate, and what it can do for you. So CL open opens a connection to the neurons and takes control of the device. The with keyword is a Python context manager, so we have right here. And basically, it guarantees that when we're done, the connection is cleanly closed automatically, even if something goes wrong. The connection object is given the name neurons. So for tick in neurons loop, ticks per second 1,000, stop after 5 seconds, this starts the main loop. Neurons loop creates a precisely timed loop that fires 1,000 times every second. That's the ticks per second 1,000, and it stops itself after 5 seconds. So you can see it stops after 5 seconds. Each pass gives us a tick object holding everything that happened in that slice of time. For spike in tick analysis spikes, and we come back up here, we can kind of just look at that and realize that can be something that we could put in here. So you can write your own code, you could write your own for loop and put it in here, and that's where we kind of get into these spike objects. So if we come down here and basically we start looking at basically the the spike objects right here, we can start to get some ideas about how we can utilize this boilerplate code right here, which is it's super important. It becomes the backbone for almost anything that you're going to be doing with the CL1. And for that section, what we're wanting to do right here is we're wanting to find and plot. We're going to plot spike. So what does that mean here? Well, basically, the import CL loads the library. Once again, the import CL loads the library. From CL util plot, import plot spike, we're able to plot the spikes that are happening. So you can kind of see the spikes here, and we're gonna run the demo here just so we can visualize that. I'll just go ahead and run it. And what this is doing for us right here is it's showing us, we're not stimulating the culture, but if we go to channel number 24, let's try to find 24. So the largest spike that was detected in these values right here was on channel 24. We can see channel 24 right up here, and we also get a graphical representation of what that spike looked like. So we can visualize it graphically here, which is very, very important. This is very important from the data science angle of this, to be able to look back and visualize. But let's jump back right up here to the code, and let's keep going. So that import plot spike imports a helper that draws a spike's waveform as a graph. With CL-open as neurons, it opens the connection, and 4 tick in neurons loop per second, basically this for loop, so once again, we're writing a longer for loop. This for loop basically runs a slow loop just once per second, because we only need to catch some spikes and not react fast. Now that's the interesting part. Spike equals max finds the biggest single spike in the tick, and you can see that right there in the data, And the backslash at the end of the line is just Python's way of continuing one statement across multiple lines. So that we can kind of ignore that in a sense there if it happens. I think it's right there. And basically, if we continue here, we begin to see that the key lambda spike, max spike samples, min spike samples defines how we measure the size. So that's right in there, right in this area. And how each spike takes its waveform samples, finds the highest and lowest microvolt value, and subtracts them. That's the peak-to-peak amplitude, the total height of the wave. Max picks the spike with the largest such value, and default is none. Right there, default is none. And basically, it means if there was no spikes at all, return none instead of crashing the program. So we saw a spike, and luckily here, it's going across all the channels, so it looked for the biggest spike, and it kind of returns it to us. And the rest, everything down from there ends up being, it's a lot of print statements. The if spike is none continue, we're able to print something out here instead of failing the loop, and gracefully close it here with a break at the bottom. But this kind of gives us an idea of it can print, for example, down here, print 75 spike microvolt values, 25 before and 50 from, labels the data, print, and then on its own prints an empty line for spacing, I believe right here, and then we get the spike samples. So the samples that are coming back is returned right here, and this is one of the great things that comes from this Cortical Labs CL import right there. So you have some wonderful tools here to sample out those spikes and get a graphical representation just built right into the CL package. Now, if we keep going down, and this is where it gets substantially more complex, but the timing accuracy with the CL API. So we look at this brick of code, and before jumping in here, we will just let's just click it and run it, and we're gonna learn. We're gonna let this piece of code run through, but we're going to also kind of explain it here. So if we jump in, the cell measures exactly how precisely API keeps time. The 3 imports load the library. Python's time module for reading the clock, as you can see, is there as well. And we didn't see very much, but I'm going to explain through this code right here, because it gives us the ability to harness this a lot better. With timing accuracy, it gives a good example here, and you can kind of see down at the bottom. Actually, we did finally get it back, and I'll explain this in a second. The microseconds that it returns in percentiles, but basically we have 4 constants. You can see right here, run for seconds 30, so it sets the test length. ticks per second is 1,000, so it's the target run rate. And then run for ticks equals run for seconds, so we take those two that we just defined right there, and then we multiply these to get the total numbers of ticks. 30,000, so it would be 30,000, 30 times 1,000, 30,000 is what run for ticks would be. Percentiles, if we come down here, is a list of percentile points that we can analyze later, chosen to expose both the best and worst cases, okay? So if we come down even one further and we go to define loop timing test, this defines the test as a function. And the line in the triple quotes right here is basically, this is just, a little doc string right here describing what it does. And, down here, loop times underscore ns np empty run for ticks, d-type int, so an integer, pre-allocates a numpy array. So we're pulling in numpy, we package numpy right here. We're pulling in numpy. And in this, let's see right here, we're pulling in numpy, so np empty run for ticks, pre-allocates a numpy array with one integer slot per tick to store timestamps. Creating it up front allows, it avoids slowdowns actually during the timed loop. Spike count 0 sets up a counter, so it counts from 0. Now with CL open, so the connection open as neurons, defining it as neurons here, we're basically opening the device. The loop is called across several lines. Tick per second is the rate. Stop after ticks is run for ticks, and it stops after exactly 30,000 ticks. Ignore jitter equals true. This tells it, so the ignore jitter right here tells it not to raise timing errors so that the test can run to completion. Okay? Inside loop times underscore ns tick iteration time dot monotonic underscore ns, basically we're recording the current time in nanoseconds into the array slot for this iteration. Time monotonic ns is a clock that only ever moves forward, ideal for measuring interviews, because this section is about timing accuracy. So in this, so we want the time to be accurate here, and this is what we're doing, and it's ideal for measuring the intervals. And the spike count down here, which is length of tick analysis spikes, adds the number of spikes to this tick into the running total. So after the loop, after we come and the loop is complete, now we report on the loop intervals. So we analyze using intervals underscore us, np, so numpy again, diff, loops time ns by 1,000, divided by 1,000, computes the gap between each consecutive timestamp with numpy using numpy diff, and then divides by 1,000 to convert nanoseconds into microseconds. NP mean, NP min, and NP max give the average shortest and longest intervals. Okay, percentiles. So we come down here, and this is where we're finally getting into the meat and potatoes of this. This is what you see down here. Okay, the percentiles output, is really important. Is a list comprehension. It loops over each percentile point and pairs it with its computed value, building a list of tuples. The print statement basically reports the results, and then they use f strings again in formatting codes like :3f show 3 decimal places, while colon, caret, so less than the less than sign right here shows 3 decimals right aligned in 6 characters, so the columns line up. Basically, the final loop for percentiles value, this one prints each percentile and its intervals in its own line, and that's how we end up right down here. And it's giving us time-based data, I believe in microseconds here, on basically looking at how many spikes per second are happening on each of these channels, and it's doing it in means, so it's showing the mean, the average of those spikes that happen, on any of these given channels. Okay, so now if we jump down to the next one, okay, this one is timing without the Cortical Labs API. Okay, so we no longer, as you can see, we no longer import that. I'm just going to run this so we get our result, but I'm going to start kind of describing, and we'll see those things printed down here in a minute. But I'll go right from the top, get it right here. So we already looked at the imports. and we'll go down to the run, so we're looking at our different items right there. And let's basically start looking at, this is basically if this cell runs the same exact test that we just did without the CL API. And why we're doing this is to prove why the API matters. The imports are similar, but as you see, you'll notice there's some difference. So if we look at our percentiles here versus our percentiles here, it's different. On the same culture. This is the same culture, but it's different. And basically the imports are similar, but notice the import GC up here, which is Python's garbage collector. So what does that mean? Which we'll be controlling in this code. The constants are mostly the same. And there's one new one, I think. Basically, if we look, I'm trying to find it, interval ns equals 1e9 ticks per second. This is the new one, and it divides 1 billion nanoseconds, which is 1 second by tick rate, giving the target gap between ticks in nanoseconds. Inside the function, loop times ns, so we see right here, is again pre-allocated. Next tick ns equals time.monotonic underscore ns parentheses, and interval ns calculates the deadline for the very first tick right now plus 1 interval. And then the for loop, basically, so we end up down here. For I range, run for ticks, loops the full number of ticks inside this crucial difference while tick ns, time monotonic tick, less than tick ns pass. This is a busy wait or hot loop. And the colon equal sign is Python's walrus operator. So we have Python's walrus operator. I'm not sure if right here. So the Python walrus operator happening there, and it reads the clock and assigns it to tick ns in the same breath, and as long as the current time is still before the deadline, pass does nothing and the loop spins, burning CPU until the deadline arrives. This is the manual way to keep time, and it's very fragile, so we kind of prefer to use API, when we can, and it's, good to demonstrate the differences here because, loop times ns, tick ns records the time it's actually fired, and next tick.ns interval right here, as you can see, pushes the deadline forward for the next tick. The analysis and print lines are the same as the previous cell, so the two results can be compared directly. At the bottom is a try/finally block, GC disable, and let's kind of come down, and it stops the garbage collector, and then it performs a loop timing test. So basically the takeaway from this output is, without the API, we could see some intervals drift by thousands of microseconds, proving that Python alone can't hold precise timing. This is a very, very specific system. I think I have some other stuff over here currently running, and you can kind of see. But it's a very, very specific system, and, you have to be very, very careful. You have to be very, very careful with what exactly we're using. And, you can see some stimulations here happening. This is kind of coming from a program, outside that I'm currently querying the culture right now, and it's very interesting. Okay, I just went and I actually disabled that program because I want to kind of keep the tutorial so we're not confusing people, but those simulations were coming from another program. It was not from this. So this is this actually doesn't stimulate right here, so just really important to note there. Kind of just came up because I have some timed recordings that happen over here, which, again, that's not quite what we're into quite yet, but it's just good to know. So I cleared it out, and the next thing we're going to get into here is and we're going to wrap up this section. So it's like we've kind of just beat the dead horse, so to speak, on hey, like, why is the CL API useful? Well, it allows us better timekeeping, best practices to keep things so they are prim and proper, for data sanitation and other purposes. Down here we're getting into basically loop timing, stability, and jitter. So what we're actually doing here, is we are deliberately, intentionally triggering a jitter error, as you can see right there. And in short, this cell basically deliberately breaks the loop to show the safety mechanism. So after importing the CL in time, right there, we can see that basically inside the single line, time sleep right here, pauses for 1,000th of a second, 1 millisecond, but at 1,000 ticks per second, each tick only has about 1 millisecond to run. So by sleeping that entire budget, we guarantee the loop falls behind. The result shown is a timeout error that shows the API can't detect the loop. Just really important to show that it's like, hey, this is the reason that the API is useful. Cortical Labs has thought this through very, very well in including these features for timekeeping, because I can say from my use of the machine, if you can't keep time, you're not going to be able to get good data, and data is everything here because hey, it is what it is. The biology behaves in very different ways than compute, other forms of compute that is. So it's just really important to be one step ahead everywhere that we can be. So it is possible to allow, we're just gonna again run this next one. It's possible, we're throwing another error here. So, we're going to look at this next one, which is accumulating a delay until buffer overflow. So we're deliberately causing another error here. But the reason is to show you, hey, like the why, okay? So this cell shows what happens if you ignore jitter but keep falling behind. We import CL, we import time, and from CL util import ordinal, I help with it turns a number like 508 into a 508, like, the 508th. Essentially it turns it into that, the ordinal helper. Ticks per second, 100, sets 100 ticks per second, and we open the connection and enter a try block so we can catch the eventual failure that we know is going to happen. So we're writing a for loop that essentially runs with jitter checks off inside time sleep, ticks per second times 2. It sleeps for twice the time budget on each tick. So the loop steadily accumulates a delay that it can't ever repay. So it's making, it's kind of getting in debt in terms of time. And what that ends up doing is it fails, and with the accept block, basically, the accept block runs, and then now neuron's timestamp gets the device's current time, frames per second, neurons get frames per second, gets the device's sampling rate, and behind seconds begins to accrue, so that accrues basically time debt, in the program that calculates how far behind we've fallen, and it subtracts the tick's start timestamp from now, and then converts from frames into seconds by dividing the frame rate. So the final print uses ordinal tick iteration, and we can kind of see that right here, which basically says the iteration failed, adding 1 because the iteration starts at 0 and then reports the seconds behind. The output shows it failed at around the 508th iteration, so that was the purpose of that ordinal call earlier, and after falling roughly 5 seconds behind, which is the size of the live read in buffer. We're going to come down even one more, and this is still yet another example. Basically, we are going to, this gets really important because there are times where you'll want to stream spikes over UDP, to assemble a UDP payload, and we're just gonna run that real quick, just to show again, we are throwing another error on deliberately here, basically, and to explain this code, we're gonna go through this here. The final cell streams spike data over the network, so import socket gives us networking, so we're getting networking here, and the import struct lets us pack data into raw bytes. Import CL, again, imports the CL library, and then CL import benchmark. We basically end up, importing the, the benchmarking from the, the timing helper, and peer equals localhost 12345 port 12345. So it's sending to that port on the localhost machine. We are, establishing our UDP socket here as socket.socket, socket AF inet, socket sock DGRAM. Creates a socket, and it means internet. The AF inet means internet addressing. Sock DGRAM means UDP, a fast and fire and forget protocol. So basically, it's ideal when speed matters more than guaranteed delivery, and that's something that's really big. When you're working with a system, you kind of have to decide Again, I'm a real big fan of the Jupyter kernel because just running things directly on the Jupyter kernel and then extracting the data later in HDF5 format, which will be another video probably. I don't think it's included in specifically this one. It actually is. It looks like it is. So pretty much perfect right there. But let's just really explain what happened here, because this is something that I just really, really want to hone in on with people is you don't always want to stream over UDP. It sounds really good to basically open a connection, start the loop at maximum speed, and then be sending a tick every 40 microseconds with ignore jitter true and everything. And it sounds good, but there's cases where you're going to be using this, and if you're relying on data that's coming from this machine, as I did in actually one of my demos recently, another video, I want to keep very objective, not be mentioning other things in this video because it is a taught and proper tutorial. We're focusing on Cortical Labs stuff, but one of the things I've found is I don't think it's a latency thing, but it is just a quirk of UDP, because you're saying that like streaming the packets is more important than them arriving, and usually that's never a problem. But if you're relying on the data coming from this machine to make some sort of assumption about how you're going to continue to stimulate or whatever, you really want to be smart and thoughtful about that. So basically, to explain, and go through this code and just really, we want to beat the dead horse here, because we open the connection, start the loop at maximum speed right here, so we're at max speed right here with the UDP socket and everything. We've gone through that. And then the first spike, it takes the first one and the payload, and it packs it into a binary string, and then basically gives it an unsigned 8-byte integer and timestamp, and then it just sends it off. And it sends off a single byte for the channel number and everything, which I think that happens right about here. But I'm a big fan of recording, and that's going to be the next video. So I think that's going to be CL-02. So our next video, we're going to get into that. But this just gives you kind of a concept of, hey, why do you need the API? Why does it make sense? How's it saving us a lot of time? Not in just the sense of the program, but just in the sense of, bookkeeping, having good data sanitation. That's what the API is designed for. And I just highly, highly, highly recommend anybody that's putting the investment into this hardware, take the extra time, go through these tutorials. If you don't know how to code and you're relying on a coding agent, it's like I thankfully came from years of Python coding. I was not the greatest JavaScript programmer, but this is all in Python, thankfully. And, I am a fairly middle of the road coder. I'm going to admit that right now to you. But through looking through the documentation and through using the tools that we have today, like AI agents and whatnot, I'm able to take this knowledge, pair it with super duper powerful coding that's coming from Claude and ChatGPT, and improve my performance and get what I really want out of the platform. So that's what I want to share with everybody. Again, our mission is to bring biological intelligence to 1 million developers. And this is how it happens, is just kind of getting under the hood, taking the extra time, working with the platform, and showing on the real biological intelligence, the benefits and pitfalls of just different approaches. So again, thank you very much. We're concluding this tutorial, and we would love to see you on the next one. So stay tuned.